I've extended the model of the CPU and added the ALU, which is capable of adding and subtracting. So I've extended the model of the CPU and added an ALU. I've also added another register. So we have register A and register B. The outputs to the registers are taken directly into the inputs of the ALU. I made a bit of a rookie mistake when designing the ALU in that I made the least significant bit at the top of the ALU, whereas in the registers the least significant bit is at the bottom. So just so that the LEDs are in the same order, this mess here is just crossing over the line, so the least significant bit is this adder here at the top of the ALU, but that is feeding into the LED at the bottom of the ALU. So the LEDs in the ALU and in the registers are in the same order. I've also added a flags register to the ALU, so we've got two more flip-flops which work in the same way as they do in the registers. We have an input switch, and then we have two flags, one for 0 and one for carry. All of the ALU's outputs are fed into a series of OR gates, and if any of them are switched on, that will feed a 1 into this NOT gate, which will be 0 if any of the switches are on. If none of the switches are on, then it means the result of the ALU's calculation is 0, and that's feeding into the 0 bit of the flags register. So if we switch the flags register on and the ALU performs a calculation where the result is 0, the 0 bit will be set. The carry out of the most significant adder in the ALU is connected to the carry bit. So if we perform a calculation where we're carrying out of the 8th bit of the ALU, then the carry out will be set. So we'll be able to check if we've overloaded the ALU by asking for a value which is too big for it to calculate. So let's test the ALU. We'll put the value 15 into register A and the value 5 into register B, and we'll see if we can add and subtract them. So we put the value 15 on the bus. That's 8, 4, 2 and 1. We switch on the input to register A and fire a clock pulse. We load 15 into register A. Then let's put the value 5 on the bus, so that's 4 plus 1. So we'll switch 8 and 2 off. And we'll load that into register B by switching on the input to register B and firing a clock pulse. Switch off the register B input and switch off the input to the bus. Now we can see the ALU has the value 10100. If I switch on the output of the ALU, that will output that value back onto the bus, and we can check to see what's on the bus. 16 plus 4, which is 20. So that's what we want, 15 plus 5. If we switch on the subtract bit to the ALU, it should now switch the input to ALU's second input to the 2's complement value of what's in register B, so that should now subtract 5 from 15. So if, with the subtract bit on and the output to the ALU going onto the bus, we can see we've got 8 and 2, which is 10 on the bus. So the ALU seems to be working. So now I'm going to test the flags register. So I'll switch the flags register input on. We can see that currently the ALU has 0 in it, and the 0 bit is set in the flags register. If we load the value, let's say 129, into register A, register A now has 129 and register B has 0. So the ALU has 129 and the 0 bit is switched off because the ALU has a value. Now if we load 129 into register B, the ALU will add 129 to 129. That's too big a number to store in a 8-bit byte. So the ALU is now overloaded. The carry bit of the most significant bit is the carry out is set, and so the carry bit in the flags register is set. So that's the flags register. So let's take a look at something we can do with our CPU model already. We'll count up in fives. So we'll load the number 5 into register B. Switch on the input to register B and fire a clock pulse to load the value from the bus. The ALU is adding the value in register A to register B, so that's 0 plus 5 equals 5. Let's put the ALU out on the bus. So now the bus contains the value 5. If we switch on the input to register A, so that register A should load the value from the bus and send a clock pulse, register A will load 5, register B will stay at 5, and the ALU will then add 5 and 5 and output 10 onto the bus. So let's send the clock pulse. And we can see now register A and B both contain 5. The ALU contains 10, 8 plus 2. We send another clock pulse. We'll load the 10 into register A, and then because register B still contains 5, the ALU will add them together, and we've got 8, 9, 10, 11, 12, 13, 14, 15 on the bus. We fire another clock pulse. We've got 16 plus 4 is 20. Another clock pulse. 16, 8 and 1 is 25. So each time we send a clock pulse, we're adding 5 and putting that value back onto the bus. So that's something we can do with the CPU model already. So in this playlist of videos, I'm going to continue developing this CPU model so that I'll demonstrate all of the major functions of a CPU at this very low level, so you can see how computers work from the ground up. If you'd like to follow the series, then click subscribe, and if you've learned something from the video, give it a like. Thanks for watching.